Hello, welcome back. In this video, we will take a look at the chi-square test. So there are two types of chi-square tests. One of them is test for independence, and second one is test for goodness of fit. We'll take a look at both in a second. So this is a very typical statistical method used for the. It's mainly about the hypothesis test. So we perform hypothesis test. It's widely used in data analysis, data science. That's one of the popular research methods. So the name is called a chi-square test. So let's take a look at what we're going to cover in this video. So first of all, what is a chi-square? We'll define the chi-square test. Basically, we compare the observed frequency with the expected frequencies. And let's see the difference among those two. There are two types of tests, goodness of fit test and an independence test. The formula we are using is a chi-square. This is test statistics. Chi-square value equal to sum of observed frequency minus expected frequency squared over expected frequency. Right. We're going to go through the calculation details, and we're going to take a look at some real-world problems with the full solutions. And we're going to learn how to use a critical value table using the degree of freedom and then significance level, which is alpha, to look up the critical value method. You can also look it up in Excel as well. And then next one is the effect size, like Kramer's V-test, right? We want to know how strong is the association if the two categorical variables are associated with each other. We'll take a look at some assumptions and then pitfalls. And we will compare the chi-square test with other tests like ANOVA, t-test, and then correlation tests, all those different tests at the end. So first of all, let's take a look at the definition of the chi-square test. It's a non-parametrical statistical test that measures how well observed categorical data matches with the expected data. Right? Observed frequency, we usually call this observed frequency, matches with expected frequency. This symbol is named after the Greek letter chi, and its chi-square produces test statistics that follow a chi-square distribution. And then the chi-square distribution looks like this. It's like a rice cube, like this. So this is a typical chi-square distribution. And then, yeah. So again, we're going to have a critical chi-square critical value here, critical chi-square value on the right tail. And then we compare the test statistics with the critical chi-square value to make the final decision. And then since it's a non-parametric test, so it works well with the count data. And then we do not assume normality in the data sets, right? So normality is not required. And then basically we work with the nominal or ordinal categorical data only, right? Not continuous data. Continuous data doesn't work. And our goal is to test independence and then goodness of fit between the categories. Now, there are two tests, right? First one is goodness fit test, goodness of fit test. The other one is test of independence. We'll take a look at the goodness of fit test. We test if one categorical variable matches with the expected distribution. So, for example, like when rolling dice 60 times, are you getting 30 heads and 30 tails? Right? That's basically, if you're getting 30 roughly 30 heads to 30 tails, meaning that each phase is equally likely. Right? And also, like, does broad type distribution match with the national data? And also, another example could be like website visit equals across all 7 days, right? From Monday to Sunday. So, for the goodness of the test, if HO, which is null hypothesis, will be observed frequency equal to expected frequency, and H1 will be they not equal to each other. Observed is not equal to expected. As you can see, because not equal to, so we are looking at a two-tail test. And then for the test of independence, we're testing if the two categorical variables are associated or independent. For example, like is the gender related to study method preference? Gender and study method, are they associated or are they independent? Does smoking affect disease diagnosis? If these two categorical variables are associated with each other. Is political affiliation linked to income bracket? That's another example. So here HO is variables are independent, meaning row variable and a column variable. Here we're talking about row variable. They both categorical and then column variable. And H1 is they are associated. So both variables are associated, meaning row variable and then column variable, they are associated. Those two are the type of test we're looking at. So the chi-square formulas, mean in order to calculate the test statistics, chi-square values, we are using chi-square equal to the sum of the observed frequency minus expected frequency. O means observed frequency. Observed. E means expected frequencies. So the chi-square test statistics using this sum is the sigma, which is meaning sum up all this square difference over E. Okay. And then observed frequencies, always observed frequency, the E is expected frequencies. Now it's let's take a look at example, right? So basically the step-by-step procedures to perform a test, which first of all we state a hypothesis. HO is that we're doing the independence test. Variables are independent or variables are associated. And we collect the data and then tabulate data, building a continuous table with observed frequency counts, right? So observed frequency comes from the real actual sample. And then from there, we calculate the expected frequencies using the row total times column total over grand total. Grand total, you can also call that sample size. Grand total is the sample size. You can also say N. Okay. And then we compute the chi-square statistic using the formula. Sum up all the cost of sales. And then for the degree of freedom for the test of independence, degree of freedom is going to be a number of rows minus 1 times number of columns minus 1. And if for the goodness of phi, we do k, degree of freedom is k minus 1. K here represents number of categories. Right, in our sample data. And decision-making process, if the p-value is less than 0.05, and reject HO, right? Or you can also say that if the test of this chi-square values, it's greater than critical chi-square values, reject HO. This one is critical value method, reject HO. So basically you draw the chi-square distribution and then you label the test. This is the chi-square critical values. So the rejection region is on the tail. So if the chi-square test statistics fall in the rejection region, then we'll reject it short, right? So if the chi-square test statistic fall in the rejection region, then reject it short. That's why this is true. Okay. So two different methods. But if you want to use the p-value method, then we're going to use technology, either Excel or like coding languages. And so here, this is the first example here. We want to determine the gender and the preferred study method, right? Test for the independence. So here, test for independence. So we have observed frequencies from sample, this is sample data. Then we have two different genders, male, female, right? As our row variables. And for the column variable, there are three different categories. There's a visual, auditory, or reading. So the first row, males, so you're adding 30 plus 15 plus 25 plus 70. The second row, you're adding female in three different categories, 20 plus 30 plus 30, that's 80. And then the column total, first column will be visual learners, 30 plus 20 is 50. And the second is auditory learners, 15 plus 30 is 45. And this is the second column total. And then the last column total will be reading learners, so 25 plus 30 is 55. Like adding the row totals, 70 plus 80 is 150. Like adding those three column totals, 50 plus 45 plus 55 is also 150. Okay. So this is also the sample size. Call this N. And then for the expected frequencies, for first expected frequencies, under the category male with visual study method, then it's going to be 70 times 50 over 150. And when we divide that, we get 23.3. The second one is auditory, so you do 70 times 45 over 150, that turned out to be 21. Okay. I have to do the calculation. And then the third one, reading for the male. Okay, so it will be 70 times 55 divided by 150. And that turned out to be 25.7 times 55 over 150. That's 25.7, approximately when you run into one decimal place. And for the female with the visual study method, that's going to be 80 times 50 over 150. So that's 80 by 3, so 26.7 when you run into one decimal place. Second category, female with the auditory learning method. So it's going to be 80 times 45 over 150. So that turned out to be 24. The last one is 80. It's a female with a reading learning method. 50 times 50, 80 times 55 over 150. Turned out to be 29.3. So this is all the observed frequency. This is all the expected frequencies. Then you do the calculations. So taking the observed frequency 30 minus expected frequency 23.3. square the difference divided by observed frequency of 23.3. And so it's going to be, there's going to be 6 different quotients here, different square quotient. So you just sum up those, and basically we get the chi-square test the physics value chi-square. That's the 6 chi-square values. And so we get 6.87 when we sum up those 6 values. And the degree of freedom here, it's number of rows. Number of rows is 3 rows. Number of rows 2, right? 2 rows. Number of columns, 3 columns. 3. So you do 2 minus 1 times 3 minus 1. So that's 1 times 2. That's why it's 2. Based on those, and alpha equals 0.05, and we go back to the table. Okay, I'm going to show you where to look up. So if you go to our Brightspace course, open the chi-square table, you see that degree of freedom 2 right here, alpha equal 0.05, okay, 5.99, right? So the critical chi-square values is 5.99. So going back here, that's why you see 5.99 here. And if you draw the chi-square test, chi-square distribution, and then we put this critical chi-square value here, critical 5.99. So this is rejection region here, and it look like the test physics fall in the rejection region. So that's why we gotta reject HO. So reject HO. Okay. So that's why because we reject HO, meaning gender and then preferred study method are associated, right? So that's our conclusion, meaning gender and then study method preference are significantly associated, okay, based on alpha equal 0.05. So that's basically the test for the independence. And also, there's a goodness fit test. Like this is one of the examples here about M&M color distributions. So the scenario is Mars claims M&Ms follow this color distribution. Red is 13%, orange 20%, yellow 14%, green 16%, blue 24%, and brown 13%. So basically, you sample 200 M&Ms. So we have 6 categories. From 6 colors means 6 categories. So K here equal to 6. 6 categories. And then the observed frequency, so you observe what's in the bag. 24 red, 38 orange, 31 yellow, 28 green, 52 blue, and then 27 brown. We add up those with the 200 M&M in the bag. And then the expected, based on the percentage for expected frequencies, so you do 200 sample size times percentage, right? So you get 200 times 13%, that's 26. And then you do 200 times 20%, that's turn out to be 40. 200 times 14%, that is 28. 200 times 16%, 32. 200 times 24%, that's 48. And then 200 times 13%, 26. So the total, again, sum up, the total is 200. So again, we do observed frequency minus expected frequency. So observed is 26 square that over expected frequency, which is 26. That turned out to be 0.15. We run the guys in place. You get a first result. Second one, you do observed frequency 38 minus 40 square dividing by observed frequency 40. So follow that formula. And then the third one will be 31 minus 28 square that divided by 28. That turned out to be 0.32 approximately. The next one is 28 minus 32 squared over 32. That's actually 16 over 32. And that's another 0.5. That's why it's 0.5. Second to the last, you do 52 minus 48 square that over 48. And that turned out to be 0.33. And the very last one is 27 minus 26 square that over 26. And that turned out to be 0.04. Now we sum up all these values, we get 1.44. That's the test statistics. And if you want to check with the critical values, the degree of freedom is a k number of categories here, 6 different colors, 6 categories minus 1, that's 5. And alpha is 0.05. And again, we take both values, go back to the chi-square table. As you can see, it's this, right? Critical alpha equal 0.05. And then degree of freedom 5, so 11.07. So that's the critical F values we're looking at, 11.07. And then chi-square is less than 11.07. So again, you draw the chi-square distribution, and then critical value is 11.07. And this is rejection region. And then the test statistics fall in the non-rejection region. Test statistics fall in the non-rejection region, so fail to reject HO. So conclusion is fail to reject HO. So that means MMDAX does not significantly differ from the claim, meaning observed frequency is equal to expected frequency, right? No statistical significance here. So that's basically meaning they are consistent, right? The MMNs are consistent from both expected frequency and then observed frequencies. Now the third example is about independence test of the independence. It's on the smoking status and heart disease. So we surveyed 500 patients and we try to figure out the smoking habits associated with the heart disease diagnosis. Let's see if that's the case. Okay. So here with the heart disease diagnosis. So first of all, we get all these observed frequencies on this table. The first one is 90, 160, 60, 190. So we get a row total. Row total, column total. Now the first, this is observed frequency. The expected frequency is going to be 250 row total times column total 150 divided by grand total 500, and then you simplify, you get 75. This is the first expected frequency. Second one, observed frequency 160. Expected frequency is going to be 250 times 350 divided by 500. Simplify, we get 175. And then the third column uses observed frequency, expected frequency is going to be 250 row total times column total 150 over grand total 500. Then again, simplify, we get 75. The last one is expected observed frequency 190, expected frequency row total 250 times column total 350 over 500. That is 175. And then after that, we do chi-square value equal to sum of observed frequency minus expected frequency squared over expected frequency. So we do 90 minus 75 squared by 75 per cell. Second 160 minus 175 squared divided by 175. The third one 60 minus 75 square that over 75. Last one 190 minus 175 squared over 175. And I sum up those four results, we get pi squared is 8.57. And again, I would have two rows, two columns. So we do degree of freedom will be 2 minus 1 times 2 minus 1, 1 times 1 is 1. And alpha is 0.05. And from here, we will look it up on the chi-square table. Go back again, degree of freedom 1, alpha 0.05, the critical chi-square value is 3.84. That's what we see from the PowerPoint 3.84. Then we can also look at the p-values, right, based on 8.57. Then you need Excel. So I'm going to just open Excel, show you how that goes. So we open Excel, and then in any cells, just type in equal to, we do 1 minus chi square. Look at chi distribution, chi-square distribution, CHISQ dot dist, and put in 8.57. That's a test statistics chi-square values. Degree of freedom is 1. And then yeah, currently everything's relaxed. Okay. But we want an area on the right here, so that's why we do 1 minus area to the left. And then it turned out to be 0.003. And that is exactly what we see from the PowerPoint here. Yep. Right, so here, 0.003. And again, because of the, if you're doing the p-value method, this is less than alpha, so reject the HO. Right? But if you're doing the critical value method, it's same result, no difference. And similarly, we will just plot a chi-square distribution and then put a chi-square critical value. It's 3.84. 3.84. And then the test statistics is 8.57. So this is the rejection region. So the test statistics fall in the rejection region. So that's why reject HO. Right. In conclusion, the reject HO indicates smoking habits associated with the heart disease diagnosis. Right. Smoking habits. Associated with heart disease diagnosis. So that's our conclusion. So that's example 3. Let's look at example 4. Again, we test for independence. Since there's more popular methods. So we're looking at the app rating by age groups. So 3 categories: age 18 to 30, 31 to 50, 51 plus, and then there's satisfied, neutral, and also dissatisfied. So very similar. We get observed frequencies, expected frequency observed, all the observed, and then expected frequency has been calculated. So then we do all the calculations. It's going to be 9 calculations here. The first one is going to be 70 minus 60 square that over 60 Second one will be 20. This is expected frequencies. The second one will be 20 observed minus expected 26.7 square that over 26.7. The third one is going to be 10 minus 13.3 square over 13.3. So let's do the calculation. Fourth one, 55 minus 60 square that over 60. Next one will be 30 minus 26.7 square over 26.7. And sixth one will be 15 minus 13.3 square over 13.3. And then last one, first one is going to be 55 minus 60 square over 60. Second to the last will be 30 minus 26.7 square over 26.7. Last one is going to be 15 minus 13.3 square over 13.3. So we add all those 9 results, we come out with the chi-square test statistic, which is 8.338%. Test statistic. So the degree of freedom, 3 rows, like under rows, 3 rows, and the column, 3 columns, 3 minus 3 times 3 minus 3, that's 4. And alpha is 0.05. And again, we look up the chi-square values from the chi-square table for 0.05, so it's 9.49. That's what we see from here. 9.49. We can also use Excel to figure out the critical chi-square values. You just have to go here and do chi-square inverse, chi-square inverse of the chi-square. And I put a probability value, it's going to be 1 minus 0.05, area to the left, degree of freedom 4. Okay. We're going to get the critical chi-square values. If you run it to 2 decimal place, it's 9.49, which is exactly what we see from the PowerPoint. 49. And then because of the test that is less than critical chi-square values, again, critical chi-square values separated non-rejection region, non-rejection. From the rejection region, this is the rejection region, and then the test size is falling in the non-rejection region, so failed to reject it. So there's no, we can also calculate p-values, right, using Excel. So you can do, so the test statistics is 8.33. Again, one more time, we do 1 minus chi-square distribution, so 8.33. Degree of freedom 4, accumulate everything to the left, and we get this 0.08. If you run it to 2 decimal place, 0.08, which is much bigger than alpha, right? It's greater than alpha. The p-value here is 8, greater than alpha, failed to reject the trade. That's the conclusion. So there's no significant relationship between age group and the absence questions, meaning all the age group have the equal, right, satisfaction level. So the company's app is equally well received across all age groups. That's our final conclusion here. And those are all examples here. And then this one has, the next slide shows you the summary of the critical value tables. The alpha could be most
popular ones are 0.05, sometimes could be 0.01, and sometimes could be something else, but all the critical values are summarized here. And also the effect size, which is Cramer's V-test. This test is when there's association, when we test for the independence, the association with the row variables and column variables, and when we know the strength, we want to figure out the strength of the association, and we apply this test, right? So this is V-test. We do chi-square values divided by sample size. Okay, this is sample size. And also K is the smaller of the rows and columns. So for that, gender study examples, we go back to gender study examples. The smaller between row and then column will be 2. Right? Row has only 2 categories. So that's why K here will be 2. K is 2. The sample size here is 150. You go back very quickly, it's 150 here, the sample size. And we apply the formula, so chi-square is 6.87. So the square root of 6.87 over 150 times 1. And it turned out to be 0.14 approximately. And then we apply the cutoff score, right? Here, cutoff range negligible is between 0.0 and 0.10. Basically, there's a little or no practical association. And then our example matches with the small associations here because the V value is V score, right? This is V value, V score. It's 0.214, which is between 0.1 and 0.3, weak but detectable association. And we have medium association, moderate, meaningful association, and also have a strong association, strong practical significance is 0.5 and between 0.5 and 1. Okay. So based on the V values, we can actually determine the strength of the association. That's quite convenient. And then assumptions and common pitfalls. So first of all, we are assuming we are using the categorical data that required variables must be either nominal or ordinal categories, not continuous values, right? Or not continuous data values, continuous measurements. Independence of the observations, meaning samples should be simple random sample, so all the data values within our sample will be independent of each other. We know repetitive measures, right, as well. And expected frequency must be greater or equal to 5. That's minimum requirements. If the expected frequency less than 5, then we need to merge categories or use features exact test. Okay? That's another story here. We also use row counts, not percentage. Into actual frequencies, right? We never use percentage or proportion. Even the percentage we convert it to frequencies, multiply by the sample size, get the actual frequencies. And also, one pitfall is association is not equivalent to causation, right? There's no causation implied in our chi-square test. It only shows, chi-square test only shows a relationship exists, but it doesn't determine the causation. I mean, it doesn't determine the cause and effect. Also, this test is very sensitive to sample size. If you pick a very large sample, and it usually produces larger and significant chi-square values, even for the trivial associations. So we always report effect size, right? Meaning we keep the sample size small. And we have comparison between chi-square test and other statistical tests. The chi-square test is applied for the categorical data, and then we look at the two plus categories: independence, test for independence, or goodness of fit. So example could be a brand choice related to gender. And t-test is applied to the continuous data and compares means of two groups on this continuous scale. Do men and women score differently, right? On the, let's say on the SAT test, something like that. And ANOVA test applied to the continuous data value as well. So we can compare means of 3+ groups. So for example, like does the do 3 teaching methods differ in scores? And correlation are applied to continuous data. So we try to locate a linear relationship between the two variables. Do our study predict exam scores, something like that. Fisher's exact applies to categorical data and typically apply to 2x2 tables with very small samples. Does a rare drug cause side effects? Right. So again, we look at a very small sample, sometimes expected frequency less than 5. McNamara test also apply to the categorical data. And then basically it's a pair repeated categorical data. So it has very narrow applications here. The attitude changes. The attitudes change before or after applying the treatment, something like that, right? So this is quick decision rule. Categorical data usually using chi-square test or Fisher's test. If we need to compare means, we use t-test or ANOVA test. If we want to determine the relationship strength and direction using the correlation test. So the interpreting and then reporting results, if you're using p-value method, p-value less than 0.05, reject HO. P-value greater than 0.01, 12 reject HO. If you're using the critical value method, so the chi-square test, if it's greater than chi-square critical, reject HO. If the chi-square test is less than chi-square critical value, then fail to reject HO. So two different kind of like approach, right? Either one is good. And then some real world applications is smoking, like in the healthcare industry, how smoking status associated with the lung disease incidence in a clinical trial. In the education sector, the pass-fail rate differs significantly between online and in-person classes. In the marketing industry, if the brand preference independent of age group in a consumer survey, and then like in the political science field, voting behavior, party choice associated with the income levels. In the biology field, does the observed phenotype ratio match Mendel's expected 3:1 genetic ratios? In the business sector, is business satisfaction level related to store location? In the psychology field, anxiety disorder diagnosis associated with sleep quality categories. Like in the sports science field, injury types distributed equally among different playing positions in different sports. In the sociology field, it's recycling behavior associated with the educational attainment level, meaning education level. So those are the real world examples, and then you can apply this method to these different fields and then get some meaningful outcomes out of it. So key takeaways, chi-square test, a quick summary, use chi-square test only for categorical data, never for continuous data. Two types, goodness of fit test, one variable versus expected, and test for independence, two variables. And for formulas, we do chi-square test is equal to sum of the open parenthesis observed frequency minus expected frequency square over expected frequency, and then expected frequency is calculated using row total times column total over sample size. Degree of freedom for the test for independence, number of rows minus 1 parentheses times number of columns minus 1 parentheses. Degree of freedom is the number of categories, that's only one category here, minus 1 for goodness of fit test. Reject HO if chi-square is greater than critical values. Otherwise, also if the p-value is less than 0.05, reject HO. And we can also add a Cramer's v-test for effect size, like different kind of strength of the association. So again, significance is not equal to causation. Large samples inflate chi-square, always report effect size. And that's pretty much everything in this chi-square test.